All right. So here we have a equilibrium problem. Equilibrium is one of those problems that some people have trouble visualizing, so we're going to run through it. We have a person on a ladder. All right, they are off center on the ladder, so 4 meters from the base or 2 meters from the wall, where the ladder is 6 meters from the wall, and it's 8 meters high. And you'll notice, of course, that it's using 6 and 8 gives us the information that, of course, it's 10 meters long. All right, because it's a 3, 4, 5 triangle, or 6, 8, 10 in this case, twice the length. Now we know that the person is 80 kilograms and the ladder is 40 kilograms. Now, for an equilibrium problem, we are concerned with 3 things. Okay? Force in the x direction, force in the y direction, and torque in the z direction. And that's a terrible torque. That's an even worse torque. Torque in the z direction. Okay? So all 3 of those things have to be adding up to 0, essentially, in order for it to be an equilibrium. Ultimately, what we're trying to find here is we're trying to find the coefficient of friction on the floor that's needed for this sustained equilibrium. Let's assume there's no friction on the wall. All right, so we have, in the x direction, what forces are applying? There's really only 2. Okay? There's the wall pushing against. And then there's the force of friction on the ground. And that's going to add up to 0. In the y direction, we got a little more stuff going on here. Okay, we've got the force of the floor upwards, force of gravity of the ladder, and the force of gravity on the person. Okay, again, there's nothing over here on the wall up and down because there's no friction on the wall. And finally, with torque z. Okay, torque z, of course, is going to take in all the forces in the x and y direction. But with torque, we have to make a determination here. Where do we want our endpoint to be? Well, we want to eliminate as many forces as possible. So right now we've got a force here, a force here, a force here, and 2 forces here. So to eliminate 2 forces, we're going to put our endpoint, our origin point here. It doesn't matter where the origin point is, it's going to work out, but that way it's going to eliminate the most. So we have, well, 0 equals the torque from the ladder. Now, again, if you calculate torque, in general, that's force cross, R cross F, sorry, wrong direction. Okay, it's R cross F. So the torque for the ladder, R goes up 5 meters. So it's 5 times the force, which is going to be 40 times 9.8. And that's going to be times sine of 37 degrees. They might ask, where did I get 37? Well, this is the angle we're looking at. And we know that this, in this kind of triangle, a 3, 4, 5, it's going to be a 53 degrees, 37 degrees, 90 degrees triangle. So we can say it's 37 degrees. That's the angle between the radial vector and the force vector. Okay? Again, we do the same thing with the person. Well, we have to do one more step for the person. For the person, we have to calculate what this radial arm is. Turns out that radial arm, with a little bit of trig, can be solved by doing cosine of 53 equals 4 over the hypotenuse of that part, and that gives us h equals 6.65. So we get plus 6.65 times 9.8 times 80 times sine of 37. Right? And finally, we have the last part, which is the wall. The wall is going to be, again, 10 meters away times the force of the wall times sine of 53. And again, that's the angle between the radial arm and the force. Now, we got a problem here. All these values are positive. We've clearly done something wrong there. Because it can't add up to 0 if all those values are positive. So, we have to accept that some of those values are different. So the way we have to determine whether they're different is we're going to say into the board is going to be negative. And so using the cross product, radial arm, force, into the board. So the first two are both negative. The last one's positive. We then solve for that and we get the force of the wall is equal to 540.4. Alright? We then take that and we can plug that in here. Oopsie. That should have been normal. Not enough friction, my bad. Okay. .4 equals the frictional force, and we can also then say that's equal to the normal force times the coefficient of static friction. So now to find US, we have to find the normal force. Okay, the way we find the normal force is from here. You know what this is? 40 times 9.8 plus 80 times 9.8. And both of those are actually going to be negative, again, because they're downwards. And that equals 0, and Fn is going to equal something I didn't write down. Bummer. See what it is? Oh, I don't know. Sorry. 120 times 9.8. There it is. 1176. Perfect. Then we put it back in here, and we get 540.4 equals 1176 μs, and μs equals 0.46. That's the minimum friction we would need for this to happen. Anything above that, and it's going to be strong enough to not slide, because again, friction can only equal the other forces. It can't be greater than them. And there it is.